Hello students. The topic for today's class is simplification of context-free grammars. So at the end of this class, you should be able to simplify your CFG by eliminating useless, epsilon and unit productions. So what do we mean by simplification of a context-free grammar? Suppose you are given a grammar G1, you can simplify the grammar by eliminating epsilon productions, unit productions, and useless productions. The resultant grammar G2 is equivalent to G1. However, if the grammar G1 does derive the null string, G2 will not be able to derive the null string because you have eliminated all the epsilon productions. So we say G2 is equivalent to G1. In this context, it is equivalent to G1 if language of G2 is equal to language of G1 minus epsilon string. The relevant theorem here is if G is a CFG generating a language that contains at least one string other than the null string, then there is another grammar G dash such that LG dash is equal to LG minus epsilon and G dash has no epsilon productions, unit productions or useless symbols and useless productions. Another thing to note over here is that the word simplification is kind of misleading. Simplification does not necessarily result in a reduction of the total number of productions. On the contrary, sometimes you may find that the number of productions has increased. We'll later on see why this process is essential. So, coming to the first type of elimination, eliminating useless productions. What are useless productions? Obviously, useless productions are ones that involve use of any useless variable. So then the next question is, what is a useless variable? Obviously, a useless variable is one which is not useful. So then the next question is, what is a useful variable? A useful variable is one which is involved in the derivation of some string, at least one string, W, in the language of the grammar under consideration. Formally, we say that a symbol X is useful for a grammar G if there is some derivation of the form S which derives alpha X beta, which derives W, where W is a terminal string. I'm sorry, this should be if, not is. So, if you remember this symbol, arrow with star means multiple steps in derivation. So, there are two aspects here. One is the right hand part of the derivation and one is the left hand part of the derivation. If a variable can, if this kind of a sentential form, alpha X beta, can be derived from S, then we say X is a reachable variable. And if from this kind of a sentential form you can derive a string, then we say X is a generating variable. Now, for a variable to be useful, it should be both generating as well as reachable. So, elaborating further, a variable is useless either because it can't be reached from the start symbol, that is, it is non-reachable, or because it cannot derive a terminal string, that is, it is non-generating. So how do we go about identifying useless variables? We identify useless variables by first identifying all the useful variables, and all the other symbols are then useless. After that, we remove all the productions which involve the use of these useless variables. Now, to remove useless productions, you must first remove productions involving non-generating symbols, then remove productions involving non-reachable symbols. So let us see an example. We have this grammar: S derives AB, S derives A, and A derives B. If we look at this grammar closely, we will see that A derives B, so A is generating. S derives A, so S is generating. That means there are only two variables in this grammar that are generating. There is another variable B in this grammar, but B is a non-generating variable. Hence, we can safely remove this production. S derives AB, giving us this resultant grammar. Now, if we look at this again, we will see that there is no way in which A is reachable from S in any derivation of any string. Hence, S is the only reachable variable in this grammar. A is a non-reachable variable. Hence, this production A derives B also can be eliminated. The resultant grammar then, after removing useless production from the original grammar, is SA. And if you look closely, you will find that the original grammar is, the language of the original grammar contains only one string. And the language of this also contains only one string. The language of both these grammars is A. So now let us look at a more formal process of identifying non-generating and non-reachable symbols. So as indicated earlier, symbol X is generating if X can derive W for some terminal string W. To identify non-generating symbols, we first identify generating symbols, and all the remaining symbols are non-generating. So to identify the generating symbols, it's a two-step process. The basis process is applied only once, and inductive process is applied repeatedly till you can add no more information or no more element in the set. So every symbol in T is generating. Obviously, terminal symbols are all generating. And if there is a production in which all the right-hand symbol, if there is a production in which all the symbols in the right-hand side of the production are generating, then the symbol on the left-hand side is also generating. Let us look at an example. We have this grammar. Now, if we are given this grammar and we would like to identify generating symbols in this grammar, we first apply the basis step. Let's call it the rule 1, and we get the set of generating symbol as AB. So if you look at this grammar, there are only two terminal symbols here, A and B. Now, now we look at all these productions one by one. So when we look at this production, A derives A, small a, then all the symbols on the right hand side of this production are generated. Hence, A is generating. So now if we look at this production, B derives AA. All the symbols on the right hand side of this production are generating. Hence, B is also generating. So we gradually increase the set of generating symbols. We perform a union operation. So now we have A, B, A and B. Looking at another production, S derives A. Now we have added A to the set of generating symbols. So hence S is also generating. Now there are no other productions that or no other variables which can be added to this set. Hence we stop. And this gives us the set of generating symbols. Now, if you look at it, there are three variables in this set, A, B, and S. The missing symbol C is a non-generating symbol. So that's how we we perform an difference operation between we perform V minus gem, and we get the symbol C. So now, since C is non-generating, all the productions involving C are useless productions and can be safely eliminated from the grammar without changing the language of the grammar. There are here two productions, S derives C and C derives ACB, which involve the use of C, and hence we can safely remove these productions and we arrive at this graph here. The next step then is to identify non-reachable symbols. Again, as stated earlier, a symbol X is reachable if there is a derivation S derives alpha x beta for some alpha and beta. So suppose we have a grammar VTSP. To compute the reachable symbols, again it is a two-step process. The first step, which is the basis process, is applied only once, and the inductive process is to be applied repeatedly. So obviously S is reachable, S is the starting symbol, hence it is reachable. Now if there is a production A alpha and every symbol in alpha is reachable. Sorry. If A is reachable, then every symbol in alpha is also reachable. Let us see another example. We'll continue with the same example. So this is the grammar that we obtained after eliminating the non-generating symbols from the grammar. Now again, we apply the basis step. So when we apply the basis step, the set of reachable symbols is containing the start symbol S. Now if you look at this SAS, that is the first production, S is already reachable, so we need not add that. Then we have SA. S is reachable, so A is also reachable. In this example, there are no other reachable variables. No more symbols can be added to this set. So what we have is A and S are reachable symbols. The symbol B hence is not reachable, and this production, which involves the use of this symbol, can be removed. And the resultant grammar then is S derives AS, S derives A, and A derives A. Before we leave this topic, I would like to remind you again that always remove non-generating symbols before removing the productions involving non-reachable symbols. If we do it the other way around, that is, if we remove productions with non-reachable variables first, we may land up with a grammar which still has useless productions. Now this is one part completed. Next, we move on to the process to eliminate epsilon productions. Now to eliminate epsilon productions, you cannot do this process directly. So for example, here is a grammar. Eliminating epsilon productions does not mean that simply delete the production B derives epsilon and C derives epsilon. Because if we simply delete these two productions, in fact, in this particular grammar, we will not be able to derive any string. So, this is a two-step process. The two-step process is that first we need to identify nullable variables, and then we need to use this information regarding nullable variables to modify the grammar in some way such that it does not contain any epsilon productions. So nullable variable, a variable is nullable if it can derive a null string. To identify nullable variable, again, it's a two-step process. If you have a if you have a production A derives epsilon, then definitely A is nullable. And if there is a production of the form B derives C1, C2, Ck, such that all these variables on the right hand side of the production are nullable, then B is also nullable. We apply this process repeatedly till we are adding no more variables to the set of nullable variables. Let's have a look at this example here. So the first step is then to identify nullable variables. Again, we have two productions using which we can apply the basis step or the step 1. We have a production B epsilon and we have a production C epsilon. So the set of nullable variables N now has, after applying the basis step, has two variables B and C. Now we need to look at all these productions. A, B, C. No, all A, B, C are not nullable. Then we look at A derives BC. B and C both are nullable. Hence, A is added to this set. Then we look at BAC. So obviously there is a terminal symbol here. So this is not nullable. And B and C obviously already are nullable. So hence we need not look at these productions. Now we need to look at all the productions again. We need to look at all the productions repeatedly till we are not adding any, or till we are, as long as the symbols are being added, we have to continue this process of looking at all the productions. So now we look at this production again, S, A, B, C. This time now, A, B and C all are nullable. Hence, S is also nullable. Now, what has happened? We have added all the symbols here. We need to continue this process till we are not adding any more symbols to the set. So we stop here and we identify that the nullable variables are S, A, B and C. Now we need to use this information to delete these or to remove the epsilon productions from this grammar. So let us look at an example which will illustrate my point even further. Once we have done this process, we have identified the nullable variables. Then the next step is to remove all epsilon productions, and we need to modify the productions of the grammar in such a way that the strings which you were able to derive from the original grammar are still derivable from the new grammar. So to illustrate this process further, just see that if there is a production A, B, C, A derives BC, and B and C are both nullable, then you can have four combinations of BC. One, nullable means that it can be replaced by null, but it can be replaced by non-null terminal symbols also, right? So it may happen that B and C both have non-null strings, or B and C both derive non-null strings. It may happen that one of this is null, and it may happen that both of these are null. So this gives rise to four combinations, one of them being epsilon. So epsilon, anyway, we are removing epsilon production, so we remove that. So looking at this, what we do is we replace A derives BC by three productions. A derives BC, A derives B and A derives C, so that all the combinations are covered. So let us see the example further. We have already identified the nullable variables here. Nullable variables are S, A, B, C. Now the production S, A, B, C, all A, B, C are nullable. Hence, we replace this one production by 1, 2, 3, 4, 5, 6, 7 productions, giving us all the combinations. All three not null, C null, B null, A null, B and C null, A and C null, and A and B. Similarly, the production A derives BC would be replaced by A derives BC, A derives B, A derives C, and A derives small a, that is the original production here. Similarly, we will have B derives BAC, BA, BC and B, and C derives CAB, CA and CB and C. And I would like to remind you of of the earlier in the very beginning, I made an observation that you may end up with more productions than in the original grammar. So this is an example where you end up with more productions than in the original grammar. Although removing of useless productions reduce the number of productions in the grammar, but removing of epsilon productions increases the number of productions in the grammar. So if a grammar G2 is constructed by the elimination of epsilon productions from grammar G1, then obviously G2 will not be able to derive the string epsilon or the null string. Finally, how to eliminate unit productions? This again is a two-step process. So first of all, what is a unit production? A unit production is one which has only one symbol on the right hand side. As you all know, context-free grammars are those which have a single variable on the left hand side. Unit productions are those which have a single variable on the left hand side as well as on the right hand side. A production of this. So such a production needs to be eliminated. This is eliminated because these productions only tend to introduce extra steps in the derivations of any string, and which is not really needed. Again, elimination of unit productions again is a two-step process. First, you need to identify what are called as unit pairs, and then you need to modify the productions. Now, what is a unit pair? A unit pair, AB is a unit pair if A can derive B using only unit productions. So, for example, you have three productions. A derives B, B derives C, and C derives D. Then AB is a unit pair, AC is a unit pair, and AD is also a unit pair. So, again, this is to identify unit pairs. Again, it's a two-step process. The basis process is that every symbol is a unit pair with itself. So, every symbol A leads to a unit pair A. And the inductive part of the process is if AB has been identified to be a unit pair and B derives C is a unit production, then AC is also a unit pair. So let us again further, after identifying unit pairs, the step 2 is that for each unit pair AB, add to P dash, that means the new grammar, all productions A alpha, where B alpha is a non-unit production in P. We'll come back to this step too with the help of an example to make it clearer. So let us first take an example. This is an example where you want to eliminate unit productions. So step one is then identification of the unit pairs. You apply the first rule. First rule is there are three variables here. So S, A, and B. So SS is a unit pair, AA is a unit pair, and BB is also a unit pair. Now, SB is a unit pair. Sorry, SB is a unit production, and you have SS as a unit pair. Hence, SB is also a unit pair. Similarly, since SB is a unit pair and BA is a production, SA is also a unit pair. Again, AA is a unit pair and AB is a production, hence AB is also a unit pair. BB is a unit pair and BA is a production set, hence BA is also a unit pair. So this is the set of unit pairs that are present in this graph. Now for the step 2. Step 2 says that for each unit pair AB, add to P dash all productions A alpha, where B alpha is a non-unit production. In simpler terms, let me show you how this is done. We have listed all the unit pairs identified in the previous step. Now, what this rule says is that if you have identified a unit pair AB, then you add to the right hand side of A all the productions which are already there on the right hand side of B. Okay. Now, when applied to SSAABB, it simply means that you add the non-unit productions of S, A, and B to the graph. So, you add there are two S productions, SAA, SB. You are applying this step, hence you add only SAA, which is a non-unit production. You don't add SB. Then AA, you add the non-unit productions. A derives small a derives BC. By the way, A derives small a is not a unit production. A unit production is one which contains a variable and on both the left and the right hand side. A single variable on both left as well as the right hand side. Here the right hand side contains a terminal symbol. Hence AA is not a unit pair. So again, coming back then, AA, and ABC. So you add these two productions here. BB. Now for the unit pair BB, you add the non-unit productions of B in this resultant grammar so that you have BB here. Now look at SB. What you do is you add, now you look at the non-unit productions. There's only one non-unit production, BBB. So to the right hand side, you copy the right hand side of B. Similarly here, you copy the right hand side of A here. AB, you copy the right hand side of B here. and BA. You copy the right hand side of A over here. So these are the set of productions in 3 dash. And this becomes your final grammar. So with this final conclusion, I want to remind you once again that when you are given a grammar to simplify, then you must follow this order of steps. First, eliminate epsilon productions. Then, eliminate unit productions. And lastly, eliminate useless productions. One more reminder here. When you are eliminating useless production, first eliminate productions involving non-generating symbols, then eliminate productions involving non-reachable symbols. So with this, we reach the end of this topic. Thank you.